Equilibrium is an important concept in chemistry. Chemical reactions are usually described using equations, and these can often imply that the reaction proceeds irrevocably in one direction only. Some reactions, however, are more complex and are in fact a balance of reactions going forwards and backwards. This balance is referred to as an equilibrium. The position of this equilibrium, how much product is produced compared to the amount of reactants that remain, is affected by several factors. Concentration. A simple example is that of an indicator. Indicators are weak acids, in which the indicator molecule is a different colour from the negatively charged indicator ion. As weak acids, they are partially dissociated into H+ and In-, standing for indicator, and these two species exist in equilibrium with undissociated indicator. If you add hydrogen ions in the form of an acid, in order to maintain the equilibrium, the number of hydrogen ions and also indicator ions from the acid must reduce, and so the equilibrium moves to the left, becoming almost entirely undissociated indicator with its characteristic colour. If you add an alkali, it reacts with the hydrogen ions, the equilibrium is pulled across to the right. More hydrogen ions need to be produced from the acid, also producing more indicator ions, leading to the indicator being mainly dissociated, and the main colour comes from the indicator ion rather than the molecule. Pressure can affect equilibrium as well. Here is a syringe containing a mixture at equilibrium of nitrogen dioxide and dinitrogen tetroxide. The syringe is capped to prevent the escape of the gas. When you apply pressure to the syringe, initially it goes darker as the concentration of the nitrogen dioxide is increased. But it soon fades and actually ends up lighter than before. This is because pressure favours an equilibrium position with one molecule of dinitrogen tetroxide rather than the two of nitrogen dioxide. When you pull the plunger out again, the reverse happens. The colour goes paler and then, again, returns to normal. And finally, temperature. The test tubes here contain cobalt chloride and copper chloride. Both metal ions in aqueous solution surround themselves with water molecules to form a hexa-aqua complex. Cobalt is pink and copper is blue. In the presence of sufficient chloride, however, a new tetrachloro complex is formed. In this case, the copper is green and the cobalt is blue. The solutions here at the start have had chloride ions added such that there is an equilibrium between the two, and so the colours are purple and a sort of cyan blue-green. One beaker is filled with very hot water and the other with iced water. Look and see what happens to the colours. You can soon see that the hot water pushes the equilibrium towards the chloride complex, the cobalt going blue and the copper going green, while the cold water favours the water complex, with pink cobalt and blue copper. If they are left to cool, both sets of tubes will return to their original colour.